Okay, the exams, just so you know, there were, what was it, 9 problems and a bonus. I graded 8 of the problems. I threw out number 2. If you got number 2 right, it was worth a bonus. Okay, number 2 is the one where it was like, find the equation line perpendicular to this line. A lot of people missed that one. So I just threw that problem out. So the way you look at this, when you're trying to figure out your grade, I mean, it's up here for you, but if you're trying to calculate it yourself, there's 80 points total possible. So if I took 10 points off, you got 70 out of 80. If you take 70 and divide it by 80, that's your decimal grade. Multiply by 100, that's your percentage. Yes? Okay, we'll keep it. All right, just if you're trying to figure out like how the points work, that's what happened, okay? You got your grades though, right? I did post your grades? Okay. Please come up and grab these. Marissa, Gracie, Justin right here, Leslie, Denise, Vincent, Gloria, you're right here. Ariel, Jackie, Jaquanda, Sarah. Oh, sorry, other Sarah. Sarah, how do you show? Valerie Ramirez. And Alicia. Chelsea. Christy. Veronica. Leonardo. Scott. Matthew. Sarah. Snow. Anisha. It wasn't in there? Okay, I'll look for it. I remember you turn in afterwards. So, okay. Tori. Nathaniel. Amber. Natasha. And Brian. All right, now, I will post the solutions to the exam in the course files, but for right now, I have the results here. We can take a look at this. Let's see how this looks here. Okay. Trying to remember how the grades, if I put the bonus in afterward or how that worked. Okay. Here's the grade distribution. There were 6 grades between a 90 and 100, so 6 A's. There were 9 B's, 3 C's, and then from there, it's 3 between 60 and 70, 2 between 50 and 60, 1 between 40 and 50, 1 between 30 and 40, and 1 between 10 and 15. So this is actually a decent distribution. I mean, considering it's pretty heavily loaded on passing grades. Would you agree? It's kind of heavy on the higher end. A lot of times my distributions in math classes look like large bar graphs on the left, not much in the middle, and a bunch on the right. So it's usually like pass or fail. Here it was a lot of passing, and then it kind of tapered off. I would say that if you lie within like that 40, if you're one of the 3 students that are between 40, 50, 30, 40, 10, 20, you may have even got a note on your test that says see me or something like that. That just means I'm concerned. All right. Everyone else, everyone is still in the ball game. It's only the first test. The class average was a 76. So that's actually pretty good, because what is a C? In a college level course, what does C mean? 70 to 80. But what does C mean? It means pass, but what's the difference between a C, B, and an A? Not number-wise. I know the numbers. Average. That's right. C means average. Okay? That's why if you're wanting to get into medical school, they don't want C's. Why? They don't want average. They want above average. So, I mean, B is above average, right? A is exceptional. I'm just being honest. That's what they want, right? They don't want average. They want above average. So to say that our class average was 75 or 76 means that the average student is average. Does that make sense? You're not thrilled? Oh, no, that's what I would expect, average to be average. I would give A's to everyone. I mean, I'm not the type of teacher where it's like I need to have an average around a 75 to be happy. I would love to see my average up in the 90s, but, this is what it is. It's math. So, anybody know what the standard deviation is? Anyone going to take stats or have had some stats in the past? Standard deviation, that's STD, DEV, that's actually a little more telling than the averages. Standard deviation tells you how far apart the grades were. I can give you a simple example. Let's just say, for the sake of me demonstrating, I only have 2 students in the class. The first student gets a 0, the second student gets 100. What's my average? 50, right? What if I have 2 students in the class, one of them gets a 25, the other one gets a 75? What's the average? Still 50. Let's say I have 2 students in the class, and they both get 50s. What's the average? 50. So the average tells you something, right? But what it doesn't tell you is that, like in the first case, my 2 students, like one of them knew it, the other one didn't know anything, right? At the 50-50, they both knew the same amount of material. So what you would have here is your standard deviation here would be large. And here, your standard deviation would be small. So the smaller the standard deviation, the more grouped together the class is. It's like you're all sinking or swimming together, To have a standard deviation of 21, that's large. That's a very large standard deviation. It means that everyone was within about 20 points of the average. Well, that means you were up at like 90-something, or you were way down at like 50-something. So that's a huge window. Does that make sense? But that's the standard deviation. Hopefully next test, the thing I like to see, I don't really care too much about the average. I care more about, can we get that standard deviation smaller? Can we get everyone together? Throw what? You might have to. I have here the high score is 115. I don't remember passing out 115 just now. So I don't know. Maybe I included the bonus later or something like that. So I'll get to the low in a second. All right. Now, so the low was a 15. All right. All right. That's it. So you kind of know from this chart where you stand. All right. What I did not include here is anything that indicates like how you are standing in the class. Like, can you still get a B? Can you still get a C? I will include that later, just not yet. Okay. At some point I'll tell you, look, if you want to try and get an A in this class, this is what you need to continue to do. A B, here's what you need to do. C, here's what you need to do. All right. Any questions on the exam? I mean, not specific. If you have like, hey, on number 4, you can talk to me usually not after class. I have to go across campus, but you can come into my office hours or call me or text me. It would say if it's right, it would say plus something. I I don't recall who got the bonus. Anyone get the bonus? What was the answer?
The answer was 2x7 minus x6 minus 9x4 or
Wait.
2
Whoa. No, not that bonus. On the test itself. On the test. 2h plus 4x plus 1. Yeah. All right. Well, again, I will post the answers. Let me do that later on today when I get back in my office this afternoon. I'll post the solutions. And that way you can go and look at them and compare them to your test and kind of see, what happened. Also, if you look at your test and you're like, hey, I did get this, or I think you took off too many points for this, you can always come talk to me about it. Because sometimes I just can't understand your work. And so I take off because I can't make sense of it. But if you can come explain it to me, then, maybe I'll give you some points back. All right. I don't have anything else on the test. But we are ready to begin a new section. All right. So let's get started. All right, we are going to get into chapter 3 here. This is a pretty intense chapter. But we're going to start in chapter 3 by doing something that a lot of you have seen already. And then after today, or maybe towards the end of today, depending on how far we get, a lot of what we'll do from Thursday on will be new to a lot of you. Which can be good because it's like, okay, I don't need to know anything from the past necessarily. This is brand new stuff. Okay, so 3.1, quadratic functions. And the applications. Oops. So let me kind of give you, before we get into the quadratic functions, let me give you kind of a roadmap of where we're going, okay? So you know what to expect over the next couple of weeks and what you should expect for our next test, all right? What we're doing now is this. We are going to look at we're going to study a total of 6 types of functions. All right, 6 total. And for all of these functions, we're going to have to know how to graph them by hand. All right, the first one we actually have already done. Lines. Okay, lines, and put a check mark next to that. I'm going to put next to it what a line looks like. You'll probably recall all lines can be written y equals mx plus b, right? But instead of using y, we use the functional notation f of x equals mx plus b. So the y is really the f of x, right? So we should all in this class know how to graph a line. The next thing we're going to do are quadratics. I'm just going to put quadratics. That's what we'll start today. And there's going to be a whole set of steps on how you draw a quadratic function. And that will be, like I said, somewhat of a review. Then we get into the new stuff. Polynomial functions. So polynomial functions are going to require a couple of steps, and they're going to, have some issues that we're going to have to remember. And the key will be that the way you graph a polynomial is completely different than the way you graph a quadratic. Okay, so there's a set of steps. For lines, you do something. For quadratics, you do something else. For polynomials, you do something else, right? And then after polynomial, we'll go into what are called rational functions. I'm just going to put rational. And these are by far the hardest ones to graph. Out of all 6, those will be the most difficult. And then after the rationals, we get into exponential functions. Those sound ugly, but they actually turn out to be pretty easy to graph. And then the sixth one will be logarithmic. Okay, and those that looks ugly also, but those are actually not too bad. Okay, so your next test after, well, this was your first test. Your next test will cover just these. Exam 2 will only be over quadratics, polynomials, and rationals, and that's all. That doesn't sound like much, but that's going to be enough. All right. Then after that, we've got a lot of other stuff that we'll do. Okay, that's where we're headed. Now, you might ask the question, you know, why do we have to graph these? And I understand that's a good question. The thing is, in the real world, okay, every one of these different types of functions is used to model things that are happening in the real world. Okay, sometimes a line is a perfect description of something that's happening in the real world. Sometimes a quadratic is a good description. Sometimes a polynomial is a good description. Whatever's happening in the real world, what we try and do is we try and say, hey, look, that's behaving like one of these. And every one of these kind of, when you graph them, you can kind of tell what's going on. Okay, I can give you some examples. If you work, let's say you make $10 an hour, let's just say. Isn't that like minimum wage, around minimum wage? No? Okay. Whatever it is. I heard in California it's $10 an hour. That's okay. Or that they were thinking about it. Who cares? Okay, so like let's say you make $10 an hour. What type of function would represent the amount of money you make in, let's say, a week? Well, you could say that the amount of money you make in a week, W, equals 10 times H, where H is the number of hours you work, right? So if I work 20 hours, I'm going to make $200. Well, that looks very much like Y equals MX. See, the H is the X, the 10 is the M, the W is the Y. So that looks like a line, doesn't it? So if you graphed it, it would look like that, and that would be your pay. So lines are good for certain things. But then if I take something like this marker and I throw it through the air like this, and I measure the time, and I say, okay, when I let it go, it went up, then it came back down, right? Yes? It went up and came back down. Then if I tried to graph something that described how high it was at a certain point in time, like if this is time, we're going to get into this, don't worry, and this is how high it was, then what happened was it went up and then it came back down like that, right? And that's not a line. So a line would not be a good function to try and model what's happening in that scenario. Okay? I mean, that's just two basic examples, and we'll talk about more later. So that's why we want to be able to graph these. We want to be able to take real-world problems, convert them into functions that we know. All right, let's get into the quadratics. All right, so when we introduce quadratic functions, we are going to introduce two different forms of a quadratic. All right, we're going to call one standard, and we're going to call one non-standard. So here's the standard form of a quadratic function. F of x equals a.
Is this a standard form?
This, I'll label it in a second. This is standard form. X minus h squared plus k, where a, h, and k are numbers. This is known as standard form. So I'll give you a couple of examples underneath this. Example, f of x equals 3 x minus 2 squared plus 5. This is a quadratic function. It is written in standard form, right?
Is that kind of like what we did with f of g and g of x? I mean, g of x.
Like a composition.
Like you're plugging it in.
You can almost see that in there that it is.
Plugged in, but I'm just saying
If you're going to look back at anything we've done and try and see similarity, you should see this as one of your toolbox functions that's been shifted around, right? This is the squaring function, isn't it? That's the one that looks like the U. That's been moved to the right 2, up 5. Okay. But that's the only connection I would want you to make from the past. Right now, I want you to look at that and be able to say that's a quadratic function in standard form, and let's identify what A, H, and K are. What are they? A is 3. You have to be a little careful with the H, because look at the way H appears in the formula. In the formula, there's a minus, right? And right here, I have a minus. So the H is actually the number itself without the minus, which would be a 2. And then K is exactly what you see, which would be 5. Y'all agree? Okay, let's do another one. Is that a quadratic function in standard form? Yes? What's A? -1, good. What's H? It's actually -4, and that's where it can get a little tricky. You have to look at this x plus 4 as being x minus -4. Isn't x plus 4 the same as x minus -4? Well, let's not get all caught up with that. The way that you can always remember H is always the opposite of what you see. So like up there, wasn't it a -2? So H was +2. Here, looks like the H inside there is a +4, so it's going to be -4 out here. And then what's K? -3. That all right?
where are we getting the -1 from?
Oh, -1 is coming from that negative in front is really a -1 in front. Yeah, anytime there's a negative out front like that, you can look at it as a -1. How about this one? Is that a quadratic function in standard form? Officially. It's a little tricky. Do you agree with this? Is that the same thing? Yeah? Okay, do you agree with this? What's x minus 0? Still x, right? So that's still the same thing? Do you agree with this? Is that the same thing? Do you see by me doing that what A is, what H is, and what K is? So A here would be -4. H would be 0, and K would be 0. So that is a quadratic function written in standard form. What I'm trying to get you to see is that you might be saying, oh, I always have to have something in parentheses squared to be in standard form, but this is one where it didn't quite look like it, but if we massaged it enough, then it can look like that. Okay. I think that's good. So these are all our standard forms for quadratic functions. Now let's talk about non-standard form. If you take the function and it's given to you like this instead, this is called a quadratic function in non-standard form. So let's take a look at a couple of examples. Also, the A, B, and C are just numbers, right? That's what I'm saying. And the A here is the same as the A from the standard form. So you'll see we're going to be able to actually convert from standard to non-standard. You can go from one to the other, one form back and forth. So the A in standard form is actually the same as the A here. But here's some examples first. You tell me, is this standard form? Is that a quadratic function in standard form? I mean, in non-standard form. Yes. Okay, what's A in this problem? -2. What's B? What's B? It's the number in front of x, right? Which is a 1 sitting in front of the x. So B is 1. What's C? C is the number out by itself. There is no number outside, well, there is, but it's not obvious, right? It's a +0. So C is 0. Why is this not like the previous form? What's the major difference between this one and the one before? There's something fundamentally different between all three of those examples and this one right here. It's this term right here with the x in it. See that x by itself? Look back at all the others that I just did. None of them had an x by itself. Now you might be saying, oh yeah, there's an x right there inside the parentheses. But the issue is that, like the x minus 2, it's not by itself and it's getting squared, isn't it? Down here in this form, you have an x by itself that's not getting squared. So the way I like to try and remember non-standard is that you have this x term in there that you don't have with the standard form. Let's do another one. This one's tricky. Is this in standard form? Do you have a number in front of x squared? What is it? 1? Good. Do you have a number in front of x? There is no x. It would be 0. Good. And then do you have a number by itself? 4. Do y'all see that? However, you could also make the argument for this problem that it's in standard form also, because you could write that as x minus 0 squared plus 4. Do y'all see that? And now A is 1, right? Here's the 1 in front. H is 0, and K is 4. So this is an example of one that's both in standard and non-standard form at the same time. It's weird, but that's the way it is. Okay. One last example here. How about this one? Is that a quadratic function in standard or non-standard form? What do you think? Non-standard? Standard? Any other ideas? Both? Both? Any others? It's neither. It's not a quadratic function. Why? There's no squareds. You have to have a squared. You have to have an x squared. See, because what you could argue here is, okay, I don't have an x squared, right? So you'd say a is 0. Would you agree with that? I mean, that's what the a would have to be, right? But let me show you something. Where's my back button? Come back over here. On both of these, on this standard form, I said A, H, and K are numbers, right? And on the non-standard form, I said the same thing. A, B, and C are numbers. There's one thing I didn't put there that I wanted to illustrate with that example I just showed you. In order for this to be a quadratic, don't you agree we have to have an x squared there? So I need to add a condition to this statement right here. Not only are A, B, and C numbers, A can't be 0. If A is 0, it's not quadratic anymore. So I want you to put underneath there, A cannot be 0. And do that up here also on the standard form. A cannot be 0. If that happens, you no longer have quadratic. Got it? So what is that? If that's not a quadratic function, what type of function is this? That's a linear function. That's a line. Okay? All right, so this is a line. All right, now that we have kind of a very, very general idea of what the functions look like when you write them out explicitly, let's talk about what the graphs of these look like. Graphs of quadratic functions. Okay, all quadratic functions have to look like one of the two pictures I'm about to draw. So I'm going to draw side by side. Your quadratic function is going to be that U-shaped thing, like this. Or it's going to go like this. Now, the U can be moved up and down, left to right. It can be real narrow, it can be spread out. But it's either going to look like a U that goes up or a U that's been flipped over. One of those two. All quadratic functions, okay? Is that all right? Here's how you can tell which one of those it is. On the left one, we will say that that is a quadratic function that opens up. Okay, we'll say opens up. And the way that we know that is if the a in the problem is bigger than 0. In other words, a is positive. So if you have a quadratic function and the a is positive number, you're guaranteed that this thing looks like a U that's opening up like that. And then it will open down if the a is negative. So if you have a -1 out there, you know that this opens down. Does anyone know what we call quadratic functions, that red-shaped U? There's another name for that. Parabolas. So I'm going to put here in green up there, parabolas. So from now on, if I say, hey, look, this is a parabola, you should know, okay, that means it comes from a quadratic function. Or if I say, hey, this is a quadratic function, you should know that its graph looks like a parabola. And it's going to open up or down, right? Now there's an important point on both of these parabolas that I want us to label. On the one that opens up on the left, notice that there is a point at the very bottom of that parabola. That would be the lowest point on that graph, wouldn't it? The bottom of the valley. That point is called the vertex of the parabola. So every parabola that opens up has a lowest point, right? Every parabola that opens down has a what? A highest point. And in either case, they're both called the vertex. You just have to know that if it opens up, the vertex is the lowest. If it opens down, the vertex is the highest. Now, would you agree that the vertex, being a point, should have an x and a y coordinate, right? So I know that to get to that point, I have to go over and then down, right, to get to that point? Or in the one over here, I have to go to the left and then I have to go up. So there's a point. There's an x and a y coordinate. It turns out that that vertex, the point, right, this point here, the x and the y, will always be HK. 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 What H and K am I talking about here? The H and K that we got from the standard form. Remember we were saying what's A, H, and K? If you have a parabola given to you in standard form, you already know where that highest and lowest point is. Let's point out some other things on this graph. We have some more interesting points. How about these points that I'm labeling here, the green ones? On both graphs, those green dots are your x-intercepts, right? So this right here is an x-intercept. Right here, this is an x-intercept. This is an x-intercept. This is an x-intercept. One more point on the graph that's interesting. This one here and this one here. That's your y-intercept. So when we graph quadratics, because remember I said the whole goal of this is for us to be able to sketch 6 functions by the end of the next couple of weeks, right? To graph a quadratic function, what we're going to do is we're going to find its vertex, we're going to find its x-intercepts, we're going to find its y-intercept, and we're going to draw it. Yes?
Can the vertex ever be the same as a line?
Yes. So yeah, that's the next thing we're going to talk about. Will you always have a vertex? Will you always have x-intercepts? Will you always have a y-intercept? Let's just see what scenarios we could run into. But this is the general picture of a parabola, okay? I'm going to bring something up here for us to play with. All right, this is a little program I wrote a couple of semesters ago. I haven't messed with it in a while, so let's see what happens here. Come on, you can do it. There you go. All right, everyone see this quadratic function? There it is. Okay, it's kind of tough to see this down here, but on the bottom here, do you see where it says f of x equals x squared? Okay, that's what x squared looks like. Now, look at that right now. Do we have, with that parabola, do we have a vertex? Yes? Do we have an x-intercept? Does the graph touch the x-axis ever? Right at the vertex, right? Right at the origin, it touches. Now, an x-intercept does not mean it has to cross through, okay? X-intercept means, does your graph ever touch the x? Now, if it crosses through, of course, it's touching, right? But it can just, I'm going to use this terminology as we move on. This one, we would say, bounces off the x-axis, right? It touches it, but it bounces back up. All right, now what I'm going to do is I'm going to adjust with this little slider over here on the side. I'm going to adjust. Let me do the K. What does the K do on the outside? Remember toolbox functions. Up and down, right? So if I move my K up and down, this is what happens, right? Okay. So check this out. If I move it here, does this parabola have a vertex? Okay. Does it have x-intercepts? How many? 2. Right? Now in the beginning we had 1 x-intercept. Here we have 2. What if I move it up here? You have no x-intercepts, but you still have a vertex, don't you? Okay. Oh, crap. I didn't mean to do that. Let me go back to the original thing. One thing we didn't talk about. We said this one had a vertex, right? This one had 1 x-intercept, and this one also has 1 y-intercept, doesn't it? Where it hits the y-axis the same place it hits the x-axis. When I moved it down, still has a vertex, 2 x-intercepts, y-intercept? Yes, it's down there at what, -6? If I move it up, vertex, yes, no x-intercepts, still y-intercept. It's going to turn out that no matter what you do, right, no matter how I move this thing around, like if I put it over here, that will have a vertex, right? No x-intercepts. How about a y-intercept? Somewhere up there it's going to hit, right? So there's 2 things on a parabola you'll always have. A vertex and a y-intercept. Always. Always guaranteed. The only questionable thing is the x-intercept. You're either going to have none, 1, or 2, right? None, 1, or 2. That one has none. This one has 1, and this one has 2. Now, what we didn't study last time is what happens if I change the A. Right now, this parabola opens up, doesn't it? Which means A is positive. So watch what happens when I switch my A now. When I let A get big, like look at, can you see what A is down here? It's 5. When A gets bigger, the parabola gets narrow, right? Real narrow. When it gets smaller and closer to 0, let me see, at 0.5, it starts to get real wide. Now, if I let it be 0, I'm going to have a problem. If it's 0, we have a line. Didn't we say that? Okay, so it's not a parabola anymore. But now, as soon as it goes negative, it flips over. So all the number front does is just changes this. It's either up or down, right? Up or down. That's it. Now, if I flip it down like this, let's talk. We still have vertex. We still have y-intercept, right? X-intercepts, 2 there, 1 there, none there. So it's still the same cases. So overall general summary is going to be what I write down now. But do y'all see geometrically what's happening? Okay. So a summary of parabola points. Let's say vertex. The vertex we will always have, right? The y-intercept we will always have. The x-intercept, it'll be none, 1, or 2. Is it possible to have 3? Can you have 3 on a parabola? 3 x-intercepts? I mean, we've said this is what a parabola looks like, right? The most it'll ever hit is 2 places. That's it. All right? So we have none, 1, or 2. Is that all right? Now, I don't want to get us too far ahead of ourselves, but what was it that we were going to study after quadratics? Polynomials. Well, here's what polynomials look like. Okay? So here, this polynomial, it appears that this polynomial hits the graph how many times? 4. Look at, this is the function right here. That's it right there. And this is it factored. And we are going to have to factor like this, which is going to be our challenge. Okay, so let me change this. I can make it like this, and I don't know, switch that around. Oh man. Look at this one right here. There we go. That's another polynomial function. So right now with quadratics, 2 x-intercepts, or 1 or none. Polynomials, it's going to be a whole other animal. And then after that, do you really want to see this or not? I didn't even ask. This is a rational function. Oh, you know what? I don't like that one.
Come on, give us a good one. Holy shit.
That's my code, sorry.
Oh, it's a code.
This is a rational function. Not trying to scare you, I'm just showing you. See the blue ones? I mean, this is what the rational function looks like. The blue right here. This green is not part of the function. That blue line right here is not part of the function. So that's an example of a rational function. But you can have something that looks completely different than that. You can have something that looks like this. There we go. There. Now you can see the blue. It looks like this. It goes up. And then here it looks like a little parabola in here. And then on the other side it does something like this. So rational functions open up. And it's a huge can of worms because they don't all like parabolas. It's like this or this and that's it. Polynomials, they look like roller coasters, you know, and they're all wavy. Rational functions can look just, every one of them is just a little different. So there's no like cookie cutter. They all look like this. Does that kind of make sense? And I said those are going to be the hardest ones for us to do. Don't get discouraged. There's going to be a set of steps. There's going to be a process. We'll get it, okay? All right, so there's our summary of the points that we can find on a parabola. The question now is, how do we find them, right? How do you find those? So how to find the points. Well, let's start off with the first thing that you'll need to get, which will be the vertex. Now, the vertex you can get pretty easily. It's just HK, right? So if you can identify it, you got it. What's the problem with that, though? Does anyone recognize we might have an issue with that? That's right. What if it's given to us in non-standard form? Right? In standard form, it's a and then x minus h squared plus k. So we have h and k. But what if it's the other form? Then we don't have h and k. So it turns out this way. H and k we'll have that right away if we have standard form. Okay, I'm going to put a check mark. That just means that we can find the vertex easily if we have it in standard form, right? If it's in non-standard form, here's what we'll have to do. If in non-standard, what does non-standard mean again? Let me write it down here. F of x equals ax squared plus bx plus c. If it's in non-standard form, then to get h and k, we have two options. Option number one, complete the square, which most students don't like. And I don't even teach much of it because the second option is a formula. And the formula is a lot easier to apply. So if it's in non-standard form, here's the formula. H will always be negative b divided by 2a. And that's it. What b am I talking about here? This b right here. What a am I talking about? Whatever that number is in front of x squared. So to find h, all you have to do is look at your non-standard form, get your b, make it negative, divide it by 2 times a. And that will be the h. To get the k, what you do is you take that answer that you just got and you plug it into your function. So this just means plug h into function. Does everyone understand that these are 2 separate techniques to find your vertex? Everyone understand that? If it's in standard form, you're ready to roll, right? As long as you get h and k correctly. If it's in non-standard form, you got to do some work. All right, next thing. We're going to do an example, don't worry. The x-intercepts. Well, we're going to find the x-intercepts the way that we always find x-intercepts for any function. Set y equal to 0. But that means basically set, didn't we call y f of x instead? So what we really mean is set f of x equal to 0. So you set the function to 0 and then you solve. Now when we solve that equation, it's probably going to require that you either factor or use a quadratic formula. But we'll have a way of getting it. All right, how do you find the y-intercepts? You set x to 0. But that really just means plug 0 into the function. Plug 0 into your function. Replace your x's with zeros. And you're done. Okay, does everyone understand, at least from this, what we'll have to do to get each of the 3 things? Vertex, x-intercepts, and y-intercepts. Everyone understand? I mean, we'll see an example, but any questions? All right, then here we go. You know you're allowed to have a cheat sheet on the test. This is probably the most important thing that you would want, because it's the procedure for sketching a quadratic function, the way that I would like you to do it in this class. Okay, how to sketch, or I'm going to say graph, because there's a difference between graphing and sketching. How to graph a quadratic function. Now, if you go to the tutoring lab to get help on this, I recommend you take these steps with you, because they will probably show you something a little different than the way I do it. And I'll try and explain my logic, and hopefully you'll agree with me when I explain it why I do it this way and not the way the book necessarily does it. What I'm saying is that if you follow their method, it seems to be, some parts of it can be a waste of time. And as a student myself, I always wonder, why do I do that? If just let me do this and you'll see what I'm saying. The first thing that you should do after you understand you have a quadratic function, okay? You first have to know that, right? This is a quadratic, not a line. The first thing you'll do is determine if it opens up or down. Now, how are you going to determine if it opens up or down? It opens up if A is what? Positive. It opens down if A is negative. Most students remember that, right? If A is positive, it opens up. If A is negative, it opens down. And you can look at it this way also. Opening up looks like a smile, right? Opening down looks like a frown. Positive people smile, negative people frown. So that's cheesy, isn't it? The second thing you'll do after you've determined if it opens up or down, is you will find your vertex. Now that might require some work, okay? If it's in standard form, HK, you're done. But we just said that if it's non-standard form, you're going to have to work for the vertex a little bit. But the step says find it, okay? So we'll find it. The third step, do a quick sketch. Quick sketch. A quick sketch just means just draw real quick what we have. Okay, what does your parabola look like? Just really fast. And from that sketch, ask yourself this question. Do you have, or do I have, x-intercepts or not? You'll be able to tell from the graph whether or not you do. If you do, if yes, find them. How do you find x-intercepts? Set y to 0. If no, move on. Move to step 4. So what do you think you'll do after you find your x-intercepts? Find your y-intercept. Right? And you'll always have that. You'll always be able to get your y-intercept. Then your fifth step, plot all your points and graph it. Some things to remember about your graph. It must be a U shape, must be symmetric. Now, I'll talk about that in a minute. There's always, yes, good question. There's always only one y-intercept. All right, you ready? We're only going to have time to maybe sketch 1 or 2, and then next class we'll pick up and do some more. All right, here's your first example. Graph f of x equals negative 4 x plus 3 squared plus 4. All right, first thing, is that a quadratic function? Yes. What form is it in? This is in standard form. Since it's in standard form, why don't you go ahead and tell me what A, H, and K are? Negative 4 for A, H is negative 3, and K is 4. Everyone got that? Okay. Now let's go through the steps. First step, determine if this thing opens up or down. 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 Why does it open down? Because A is negative 4. That's less than 0. And so I know this opens down. Let me just ask you real quick. If it opens down, then do we have a highest or lowest point? Highest, right? The vertex will be the highest? Okay. Now step 2. Let's find the vertex. The vertex is straightforward, isn't it? It's HK. It's negative 3, 4. So far, this all right? Third step is a quick sketch, isn't it? Quick sketch. So I'm going to do a quick little sketch here. And to do my quick sketch, I'm going to start by plotting the only point I know. The only point I know is what? The vertex, which is negative 3, 4, which means to the left 3, up 4. 1, 2, 3. 1, 2, 3, 4. I know that that point is on my graph. But it's not just any point, right? It's the highest point, isn't it? So that corresponds back up on that picture I drew up there. That's that black dot right there. So my graph must do what from there? Go down, right? So if my graph goes down from here, right? This is a quick sketch. I can look at that and just tell right now that I should get how many x-intercepts? 2, right? Do y'all see that? So I should have 2 x-intercepts. Now this is where I was saying, if you go to the tutoring lab, they might do a little different, because usually at the tutoring lab, they make you, well, most books will say just try and find the x-intercepts without any knowledge of whether or not you have them at all. Here we have them, right? So we should go try and find them. What if it opened up? What if we got to this step, our vertex was the same place, but it opened up? You don't have x-intercept. So why go waste your time going to try and solve an equation that's going to have no solution? Right? It saves you a lot of time. Because they want you to see that when you solve the equation, you get like imaginary number answers. You'll get a negative under a square root or something like that. I just say, why even mess with that? So this is the way I do it. Now, we have 2 x-intercepts. So since we have them, we need to find them, right? And how do we find x-intercepts? Set y equal to 0. So here I go. I'm going to set my function, which was negative 4 x plus 3 squared plus 4 equal to 0. I have to solve this equation. Right? I have to solve that. Now, listen carefully. When you are in standard form and you're trying to find x-intercepts, you will always get something that looks like this, right? And the way you solve this should always be the same. The way I'm going to do this, all right? This is what you should do every time you're trying to set a standard form quadratic to 0. First thing, I'm going to try and get this right here with this squared by itself, isolated on one side of the equation. So first I will take the plus 4, subtract it on both sides. So subtract 4, subtract 4. I'll be left with now negative 4 sitting in front of x plus 3. That quantity squared equals negative 4. Now what? Divide by negative 4. If I divide both sides by negative 4, on the left side it becomes a 1, and so it's really just not there anymore, right? It's just sitting out in front. On the right side it's 1. Now square root property. Good. So the whole goal is to try and get that thing squared by itself so we can now come in with square root on both sides. So I'm going to come in here, I'm going to go square root of the left side equals square root of the right side. And I'm forgetting something extremely important here, plus or minus. Now, here's the story on that plus or minus. Remember it this way. Anytime you take the square root on both sides of an equation, you come in there and you do it physically, you come in square root both sides, you must include a positive or a negative. And I can just show you a quick reason why. Look at this equation here. X squared is 4, right? If I just say square root, and go x equals 2, that's correct, right? I mean, x squared equals 4 was what I was trying to solve. If I plug 2 in there, it's right. 2 squared is 4. But you're missing an answer. Negative 2 squared is also 4, right? Negative 2 times negative 2. So you missed that unless you had put that plus or minus on there. Then you said plus or minus 2. Then you get both solutions. So when you were at this step here, you have to put that plus or minus in front of the square root of 1. And so now we have this. What is the left side? So the whole idea of taking the square root of something squared is that they cancel each other out. We're left with just x plus 3 equals, the square root of 1 is 1. So plus or minus 1. You need to understand that that plus or minus 1 means there's two scenarios here, two cases. One, you're going to treat it like a plus 1. The other one, you're going to treat it like a minus. So now what I'll do, I'll subtract 3 from both sides. And watch the way I do this. This is, again, very critical. The left side becomes x. The right side becomes plus or minus 1. And I'm going to take 3 away from it. So I'm not going to do 1 take away 3 and get like negative 2 or anything like that. I'm just going to leave it like this. And then I'm going to look at the two cases. Positive 1 take away 3 and then negative 1 take away 3. So I like to draw little arrows out like this. And I like to say, here's what I do if I have the plus, and here's what I do if I have the minus. So let's treat the 1 like a plus 1. What's plus 1 minus 3? Negative 2. What's negative 1 minus 3? Negative 4. These are my two x-intercepts. We're running out of time. All right, questions? Next step. 4. Y-intercept. How do you find the y-intercept? Plug 0 in for x, right? So for us, it's negative 4, 0 plus 3 squared plus 4. Right, isn't that the original function, me replacing the x with 0? That's the same as negative 4 times 3 squared plus 4. 3 squared is 9. 9 times negative 4. Negative 36 plus 4. Which is negative 32, right? Do you all agree? Just remember, when you do this, you have to square the 3 before you multiply by a negative 4, right? You don't go negative 12 squared. So negative 32. That's it. We're ready to graph. Here it comes. Now, with these graphs, we need to make sure we have all the points plotted correctly. So I have negative 3, positive 4. There's my vertex. Where's my x-intercepts? Negative 2 and negative 4. Do y'all agree? And then negative 32 is way down here, isn't it? Way, way down here. Now, I'm not going to count this out. Well, I could. Let's just say it's down here. I'd have to count 32 slots down, right? There's a point there. Now, what you need to do is draw your U through those. So I'm going to do it like this. Here's my U up here. Make sure it's a U, not a V. See that U up there? And then I've got to come down, and I've got to cross through that y-intercept there, like that. And this is where I was talking about being symmetric, right? What did I mean by symmetric? Here's what symmetry means. Same on both sides. If I take an imaginary line that goes right down the center through the vertex, right down the center like that, my parabola should look like a mirror image on the other side. Like something like this. Not like this. You know? That's it. I tell you what, I have to let you go because, wait, no, 45, right? 10:45? I don't know why. Hey, my Cal 2 class ends at 12:40, so I always mixed up. Okay, let me give you a couple of problems to do for homework. The homework's not going to come out of the book. All of these I want you to graph. This one's going to be hard. That last one. Not hard, but let me just give you kind of a hint on number 4. On number 4, when you do that square root on both sides where you have to do plus or minus, when you do that, the square root of that number is not going to be a number you know. So like on the problem we just did, we had square root of 1, didn't we? Square root of 1 was 1. On the other problems, the square root's going to be nice. But on number 4, when you do that square root, you won't know it. So you're going to need your calculator and get it as a decimal. Okay? So see how you do on these 4 problems. All right? I'd like to see them when you come into class next time. So have them, see how you do. Good luck. Have a good week. No, not weekend. Shoot, it's only Tuesday. Oops. Getting a little ahead of myself there.